So now we are going to discuss this isoparametric formulation. So isoparametric formulation, let me take an example. Isoparametric formulation. So I am taking an example. Let us see. I am going to take two elements. Let us take this is node number 1, node number 2, and let us take this is node number 3, and this is x1 y1, x3 y3, and here x2 y2. Now another element I am going to take, that is 1, 2, 3. Again here x1 y1, x2 y2, and x3 y3. And let me, so this is direction, I am taking zeta, and here I am taking eta. Direction, this represents this eta and zeta represents that we have taken in natural coordinate system. So this is in natural coordinate system, I can say natural coordinate system. And here x direction and y direction we have taken, this is x direction, y direction. So this is in global coordinate system, global coordinate system. I hope you people know what is global coordinate system and natural coordinate system. Already we have discussed these things earlier. So this is global coordinate system, this is natural coordinate system. So see, isoparametric formulation. So what elements, this, let me write one more thing. This element I am going to represent this as original element. Original element, and this element I am going to represent it as isoparametric element. Isoparametric element. So now what does it mean, isoparametric element? Why I have taken this as original element? Why I have taken this as a isoparametric element? So isoparametric elements means what? The elements whose shape or geometry and field variables, means either it is shape or geometry, both are same, right? Field variables like displacement and all are described by the same interpolation function. Same interpolation function, or we can say that shape functions. You know, if you are not able to understand the interpolation function, shape functions, you are aware of these shape functions, right? So the elements whose shape and field variables are described by shape functions of same order are specified as isoparametric elements. Means if we have element, we have two elements here. See, element number 1 that I have considered as original element, and element number 2 that I have considered as isoparametric element. If we'll see the geometry of this or shape, both are represented by the coordinate x1 y1, x2 y2, and x3 y3. Means coordinates are same. Next, field variable. So if I will take the displacement at this u1 v1, here also I am going to take u1 v1 also, right? That is also same, and both are represented by the same shape function of same order. If the shape function of these two elements are same, of same order, then we can say this is called as isoparametric element. So this can be transferred into this type of element, this original element. This original element, if you will see, this original element is curved one, right? The sides are curved, so it will be difficult to analyze this. It will be difficult to analyze this type of elements. So we have converted this element into the simpler one, in which the analysis will be easy. So the what is the main theme of this isoparametric elements? So the principal concept I am going to say is that isoparametric finite element formulation is to express the element coordinates and elements displacement. Elements coordinates same coordinates I have represented, elements displacement in the form of interpolation, or I can say shape function, right? Both are same, using the natural coordinate of the system of the element. Natural coordinate, see here the thing is in global coordinate only. I have to convert the coordinate system. I have to, if the original element is in global coordinate system, I have to convert the system into natural coordinate system. These isoparametric elements of simple shapes means what? Simple shapes, whenever I'm simple shapes means straight. This is not simple shapes, this is complex. This is your complex structure, complex element, because this is not simple, this is curved, the sides are curved, and here the sides are straight. That's why it is simple elements. I can refer this as simple elements. So I can say these isoparametric, this I am telling about this isoparametric elements of simple shapes. Why simple shapes? Because the sides are straight, expressed in natural coordinate system. Obviously this is expressed in natural coordinate system, is also known as master element, this also we can say this as master element. We can also this say that it is also called as master element. So what are these? These are the transformed shape of curved sided finite elements of actual system expressed in global system. So why we are saying this as a master element? Why this is a isoparametric element? Because this isoparametric element is the transformed shape. Transformed shape of what? Because this is transformed. From where to where? From here, the first shape to second shape. That is why it is called as isoparametric element or master element, because it is transformed from what type of structure, what type of element? Curved sided finite element. Curved sided finite element, or we can say that complex. Means isoparametric formulation in very simple way. These all are the technical definition. In a simple way we can say, if we have a complex element and we are transforming that complex element into a simpler element by changing its system from global coordinate system to natural coordinate system, that element is called as isoparametric element or master element. I hope you got the point. I will repeat once again. It is nothing, isoparametric formulation is nothing if we have a complex element. What we have this? A complex element. Complex, how will you identify the complex element? If the sides are curved. So if we have a complex element and we have to convert, and we have converted this complex element into a simpler element by changing its coordinate system from global coordinate system to natural coordinate system, that element is called master element or isoparametric element. And this whole process is called isoparametric formulation. So this is all about the isoparametric formulation. Based on this isoparametric formulation, we are going to see the isoparametric formulation of a CST elements. So let us discuss for CST element. Isoparametric formulation for CST element. So let us take a triangle, constant strain triangle. We have a constant strain triangle. Let us take, this is node 1, this is node 2, and this is your node number 3. Let us mark the, this is U1, V1, U2, then V2, sorry, this is V2, then here U3 and V3. We have this CST, and let us take any point P inside this element. Let us take a point P inside this element. Let us say this is U, at that the displacement is U and V, and coordinate is XY. The coordinate of this P point is XY, and the displacement is U and V, and here these are the nodes. I have taken a point inside that element P, and we are going to find the displacement at that P point, U in direction X, U and V. What will be that? U and V. So now for CST, we know from the shape function, for CST element, we know from the shape function, we can write U as N1 U1 plus N2 U2 plus N3 U3. N1, N2, N3 are your shape functions at node number 1, 2, 3. N1, N2, N3. Similarly, V can be written as N1 V1 plus N2 V2 plus N3 V3. So U and V can be written by using the shape functions relation. We can write U can be written as N1 U1 plus N2 U2 plus N3 U3, and V can be written as N1 V1 plus N2 V2 plus N3 V3, where N1, N2 and N3 are shape functions. Now, what will be the value of N1, N2 and N3? Already we have derived in the shape functions of CST elements. Let me write a common equation. So Ni can be written as alpha I plus beta Ix plus gamma I y upon 2a. Now from here, if you want to calculate N1, in place of I, keep 1. So alpha 1 plus beta 1x plus gamma 1y upon 2a. N2, alpha 2 plus beta 2x plus gamma 2y upon 2a. Similarly, if you calculate N3, just in place of I, you keep 3. So I have written a common equation. By using this common equation, you can find N1, N2, N3. So no need to remember N1, N2, N3 separately. Just you remember this equation. Once you will remember this equation, whether you are going to find N1, N2, N3, it will be easy for you. Now location at the point P. At P point, if you will see, the coordinates are X and Y. So how we can write this X? See, X means what? In which direction? U direction. So if I am going to write here that X, so how I can write this X? At P, X we can write in terms like N1 X1 plus N2 X2 plus N3 X3. Similarly, if I am going to write Y, how can I write? See, U can be written as N1 U1. So similarly here in X direction, U is there, right? So in place of U, if I will write X, so what will happen? N1 X1 plus N2 X2 plus N3 X3. Similarly, if you want to write Y, what you can write? N1 Y1 plus N2 Y2 plus N3 Y3. And we know that the sum of shape function is always 1. So N1 plus N2 plus N3 will always be 1. The sum of shape functions of any element will be 1 only. For beam element also, the sum of shape function are going to be 1. For bar element also, sum of shape functions are going to be 1. For CST element also, the sum of shape functions are going to be 1. So here shape function is N1, N2, N3. So in place of N1 plus N2 plus N3 is going to be 1 only. So from here, if I take the equation for N3, let us take, I am making M3 as subject. So what will happen? 1 minus N1 minus N2. Now, if you will put these things in these two equations, here and here. So what we are going to get? So in place of N3, we are going to write 1 minus N1 minus N2. So this X will be N1 X1 plus N2 X2 plus N3. In place of N3, 1 into X3, that will be X3, minus N1 into X3, N1 X3, minus N2 into X3, N2 X3. So see, these, from these two we can take N1, N1. Yeah, from these two we can take N1 common. So what will be left? X1 and X3. So I can write X1 minus X3 into N1 plus X2 minus X3 into N2 and plus X3. Similarly, if I will put it in this equation, we are going to get Y as Y1 minus Y3 into N1 plus Y2 minus Y3 into N2 plus Y3. So this is the formula. This is the formula for finding X and Y, X coordinate and Y coordinate at point P. If they are asking you to calculate X and Y, we can calculate by using this formula. How to calculate X and Y? Suppose they are asking you to find, suppose everything they will give and they will not give you this X and Y, they will ask you calculate this coordinates X and Y. So directly you can find by using this formula, right? So this is isoparametric formulation. Since we can find this X and Y by using shape function also, but this is the direct formula. Directly we can find this. Just we need to put all the values here, N1 value, N2 value, X1, X2, X3, and we are going to get that X. And this is the isoparametric formulation. This is the formula for CST element for isoparametric formulation. Based on this isoparametric formulation, we have one more concept, that is the concept of isoparametric, superparametric, and subparametric elements. So isoparametric, superparametric, and subparametric. What are isoparametric, superparametric, and subparametric elements? So let me draw that first, so that will be, let me mark this as, let me mark the nodes, and then similarly here also. Nodes 1, then for sub, okay. And the most important thing, let me write what is this dot mean, and this square I have made, or a rectangular, that representation, what does it mean? So let me write this here, dot, what does it represent? And this box, what does this box represent? Okay, this dot represents nodes for defining displacements. This is for nodes for defining displacement. And this box represents nodes for defining geometry. Nodes for defining geometry. Now, on the basis of this, you can write the difference between isoparametric, superparametric, and subparametric. See here, if you will see in the case number 1, that is isoparametric. In isoparametric case, see how many dots are there? 3 dots. 1, 2, 3. How many boxes are there? 3 boxes. 1, 2, 3. So in this case, we can say this dot is equal to box. Dot is equal to box means what? Dot is equal to number of defining displacement is equal to, sorry, no, number of nodes for defining displacement is equal to number of nodes for defining geometry. This number of nodes for defining displacement is equal to number of nodes for defining geometry. Both are equal, then it is called as isoparametric. Now, what is this nodes for defining displacements? Means if you want to define the displacement in this element, at least we need 3 nodes, that is 1, 2, and 3. And even for defining geometry also we need at least 3. Means you can take even more than that, but minimum requirement is 3. That is not maximum, right? The minimum requirement is 3. By these 3 nodes, we can define the geometry of this element, and we can define the displacement of this element. So that is called as isoparametric element. Coming to superparametric element, see the number of dots. Now in this case, dot is less than boxes. In this case, dot is less than boxes. Means in this case, the number of nodes for defining displacement is less than the number of nodes for defining geometry. So if you want to define, suppose this is 1, 2, 3, and then we have additional things. Additional means here we have, let us write, sorry, this will not be visible. So let me write it as A, B, and C. So if you will see, these boxes are 6 and these dots are 3. So here now nodes for defining displacement is less. So the number of displacement nodes required for defining the displacement in this element is less as compared to number of nodes required for defining this geometry. Because if you want to define the geometry, we need some displacement, right? If you are talking about the CST elements, we are taking here 3 nodes, and we are saying n1, n2, n3, and these all are safe functions. Means by only these 3 nodes we are able to define this geometry. But coming to LST, we have 6. LST we have 6, so we need 6. Suppose n1, n2, n3. Let us write some element is like this. In that there are 6 nodes, same, but in that to define the geometry we have to take at least 6 nodes. So here what happens, the number of nodes required for defining the geometry is more as compared to this case. So similarly here, if number of nodes for defining displacement is less than the number of nodes for defining geometry, then it is superparametric. Coming to subparametric, you might understood in this case, what is this dot is greater than box. So here for displacement, for defining the displacement in this element, we need more number of nodes as compared to the nodes for defining geometry. So here for defining geometry only we need 3, 1, 2, 3 only, but for defining displacement we need additional 3, that is, let us take total 6 ABC, right? So this is the difference between isoparametric, superparametric and subparametric element. This is completely based on the number of nodes for defining displacement and the number of nodes for defining geometry. On the basis of this thing only, we will decide whether the given element is isoparametric element or superparametric element or subparametric element. And this is very, very important. Coming to theoretical questions, this question is very, very important in this subject. Okay. So next we will discuss the problem itself. In this, the theories are okay. Already we have discussed all the theories. Now only we need to solve the problems. Okay.